Right? Let's continue proving Simon's six-flow conjecture and the theorem, which states that graph with no cut edges have Nowhere-zero six flows. And in the previous lecture, we showed that we can actually assume that graph is simple, three regular, three connected. Okay. Now, the idea of the remaining of the proof is to find the sum set of edges x, so that outside of x, we have a G3 circulation, phi 1, having non-zero values. This is G3 circulation of the graph G, which has non-zero values outside of x. And the inside of x, you can find the G2 circulation, so that inside of x is non-zero. If we can prove these two things, then we can combine them, and that will be Nowhere-zero G3 times G2 flow. And 3 times 2 is 6, therefore by Tutt's theorem you will have a 6 flow. Okay, so that's the idea. So to implement this idea, let me define something called the closure. So for a subset x of g, let closure of x be the minimum set y such that, so when I say minimum set, it's a set of smallest size satisfying the certain properties, such that y contains x and there is no cycle C of g with the EC minus y. So when I remove y, then you have exactly one or two edges outside. So you don't have any, so here's x, here's y. You don't have any cycle that uses only two edges outside or one edge is outside. This kind of thing is forbidden. And you want to find the smallest set having such a thing. So in other words, equivalently what you can do is you start with x, and whenever you find a cycle which has one edges, or whenever you have a cycle having one edges, you add it into x. You add it into y, and you keep doing. You keep finding a cycle where you have only one edges outside, all of the edges are inside x, then you add it to y. If you have a cycle where you have two edges outside, you can add it. You continue doing it. Eventually, you end up with a sum set y, where there's no further cycle having only one or two edges outside. That set is closure. Let us write it as a C at x. Okay? Now, here's the claim. If closure of some set x is set of all edges, then G has a G3 circulations phi such that phi of E is non-zero for all E outside of x. Okay, so if I happen to have a sum set x where you can keep adding cycles having only one or two edges outside, you keep adding those cycles, and eventually if you can make a whole edges set, then the claim is that you have a G3 circulation that we wanted. How do we prove that? We prove by induction. So suppose not. By induction, I mean, I will think of the count example with the maximum x. So let x be a count example. With the maximum size of x. Then clearly x is not equal to set of whole edges. right? Because if it does, then the closure of x is trivially E of g. And by the definition of closure of x, so x itself is not a closure of x, so therefore there is a cycle right? So x is not a closure of x, so that means that there is a cycle C such that C minus EC minus x is 1 or 2. All right? Now, let x prime be the union of x with EC. Now, closure of x prime is again, this must contain, this must contain closure of x by definition, right? Because if you look at the definition of closure, it's a minimum set Y containing x with a certain property. And now I'm asking a minimum set Y containing x prime. X prime is a superset of x, so it should be harder, right? So, but this was E of g, right? So therefore, closure of x prime is E of g. Now, x prime is no longer counterexample because of the assumption. Right? We chose x to be the counterexample with the maximum x. So, there is, so by the assumption of x, x prime satisfies claim. And so there is a G3 circulation phi such that phi of E is non-zero for all edges not in x prime. Right? For all edges not in x prime, you have non-zero values. All right, so here's a cycle C, and there were like 1 or 2 edges, maybe 2. Let's orient, to simplify the argument, let's orient in the same directions. And this was, these 2 edges, maybe 1 edge is not in X. Now, how can I make these 2 red edges to be non-zero? Right? I mean, what could be possible is probably maybe both could be 0, or maybe one of them is 0, the other is maybe plus minus 1, or this is 0, and the other is plus minus 1. This is possibilities. Or both of them are non-zero, right? Yeah, I could have written plus minus 1. Anyway, this is possibilities, right? Possible values of phi for those 2 edges not in X, but in C. All right. Now, what do we do? If this is the case, then we are happy because phi of E will give phi of E is the circulation, G3 circulation that we wanted to find. Right? So this doesn't happen because the X is counterexample. Right? There's no G3 circulation where outside of X is non-zero. So one of these things will happen. Now what we do is we just add something over this cycle. So let phi prime via G3 circulations of G such that phi prime of edges is plus minus 1 if E is in the cycle and 0 otherwise. Right? So just follow this cycle and you put 1 if it's the same direction, you put minus 1 if it's a different direction. That's the circulations, right? Now, if I add, notice that if I add a plus 1 here, then this will be non-zero. If I add a plus 1, this will be non-zero. If I add a plus 1, this is non-zero, but this will become 0. In that case, I'm adding, subtracting it. Then this will be minus 1, this is minus 2, which is the same as 1. In this case, I add a 1, 1, so it's 2, 1. In this case, I'm subtracting 1, so 1, 1, right? In all cases, one of these three choices, then phi or phi plus phi prime or phi minus phi prime. At least one of three is a G3 circulation having non-zero values outside of X and contradiction. Okay, so that's the proof of the claim. So we claim that if the closure is everything, then you have circulations where outside of X you have non-zero values, and that's true. Now, let me remind you that our idea, we want to find the set X set that outside of X I can make a G3 circulations having non-zero values. Inside X I can make G2 circulations with non-zero values. But how do we make a G2 circulation with non-zero values? You just need a collection of cycles. Imagine, since graph is 3 regular, you don't have any two cycles overlapping, right? All the cycles will be disjoint. So what we want to find is actually vertex disjoint cycles, right? So the goal, now the claim 2, there is an edge set of vertex disjoint cycles so C such that closure of C is everything, right? If this claim is true, then we are done, because C is already a vertex disjoint set of C is already an edge set of vertex disjoint cycles, and you can find the G2 circulations where on the cycle you get a 1, and outside of cycle you get 0 trivially. And outside of cycle you can cover them by using the previous claim that you make non-zero values outside of cycle, and when you combine them together you have a Nowhere-zero 6 flow. Okay, so how do we prove that? Proof. Yeah, so we choose an edge set C of vertex disjoint cycles and a connected subgraph H of G with a set of edges of H is in the closure of cycle such that, right? So we start with the edge set C of the vertex disjoint cycles, and then I take a closure of that edge set, then you will have something. And take one component of that. That will give me a connected subgraph. That's H. And there will be many choices of C and H. Among all the choices, I will choose the one that H is maximal. Okay? So you have a list of cycles. So maybe I just draw over here. And then take a closure, and H is a connected subgraph contained in the closure. Okay? Now we choose H to be maximal. Since H is connected and E of H is in the closure of C, H, yep. And E of H is in the closure of C, we deduce that H is an induced subgraph of G. Okay, what? Why? The thing is, if H is not an induced subgraph, if not, what's going to happen? I have so here's an H. Here's an H which is not contained, right? So H is connected subgraph, and let's say these two vertices are in the same H, but this dotted edge is not in H. Now, if this is in the closure, then I can easily add E and still maintain connectedness, and then that's a contradiction to the maximality. So what's left is to show that this edge E is in the closure. But why is it in the closure? Because I have a path connecting these two vertices, because H is a connected subgraph. And all these edges, the black edges in the path, are contained in the closure of C. Now, there is a cycle, right? So you have a cycle C, which has only one edge outside of the closure, which is contradiction, right? The closure of C has the property that there's no cycle having only one edge is outside. So H is not an H. So H has to be induced subgraph, right? All right, so H is induced subgraph. Furthermore, there is no vertex V in V of G minus V of H with two neighbors in H. Why? Here's the H. Now it's induced subgraphs. If I have two vertices, two neighbors, what can you say? Well, still same, right? I have H is connected, so I have a path connecting these two inside H. Now we find the cycle having only two edges outside of H. And those two edges should be contained in the closure of C, right? So those two edges should be in the closure of C, right? So that's it. So that means I can add these two edges to H, right? Adding these two edges to H still make a connected subgraph contained in the closure, and that's contradiction to the maximality of H. So there's no vertex outside of V having two neighbors, having at least two neighbors. All right. Now, we may assume that okay, E of C is subset of E of H, because, well, if you have a cycle outside of H, even if you delete it, you still have the same you still have a closure covering H. So we can assume that, right? Why not? Just by removing unnecessary cycles. Now, what's left? We will try to find a cycle outside. So then we wish to find a cycle D in Vg minus Vh that has at least two neighbors of Vh. Okay, that's now our goal. Why? Well, so here's a C, here's a H. If I have a cycle D having two neighbors, then what can you do? Well, that means that already gives me something like this, where this is a cycle having only two edges outside of the closure. Oh, I mean, this is what I mean. The closure of C union D contains edges of H union edges of D union those two edges. Let's say E1, E2. And this gives me a connected graph, connected subgraph of closure, which is bigger than H. And that's contradiction to the maximality of H. Okay? So that's the next goal. How do we find it? How do we find the cycle having two neighbors of H? Now, that's where we're going to use maximum degree. No, degree conditions. Every vertex is degree 3. All right. Now, if G delete V of H is 2 connected, then what can I say? This is the simpler case, right? Outside is 2 connected. And graph itself is connected. Actually 3 connected. Right? So what does that mean? H, D, graph is 3 connected, so you must have at least 3 edges here crossing, right? No, not D, outside of V of H and complement. I can always find 2 vertices. I need to use, since G is 3 connected, there are 2 vertices xy not in V of H having neighbors in V of H. Why? If you don't have 2 vertices, let's say you only have 1 vertex having neighbors, then this will become a cup vertex, right? That will separate the graph. and that's contradiction to the three connectedness. I mean, we don't even use three connectedness. You're only using two connectedness here. Anyway, that's good. That's enough. So I have two vertices, and graph is two connected, so I can find the cycle containing x and y in, and G minus V of H has a cycle D containing x and y, because that's the property of two connected graphs. So that's it, right? You have a cycle D having two neighbors of V of H, right? So that's one case. That's easy case. So we can assume the graph is not, G delete V of H is not two connected. If G delete VH has like only one vertex, okay, what if this is at most 2? Again, same method. No, is it? Is this easy case? If you have only 2 vertices here. Oh, actually, I'm not finding. Alright, so every vertex has degree 3. Okay, every vertex has degree 3, so each vertex has degree 3. So even if they are adjacent, you must have at least 2 neighbors. That's contradiction, right? Because we said we can assume that every vertex has at most one neighbor in H. No vertex has 2 neighbors in H. So that means, so we may assume G delete V over H has a cup vertex. C, let's say. Now, right? Okay, cup vertex. You have a cup vertex C. Why do I care? Remember, we had this block decompositions, right? So we can partition graph, the edge set of graph into by the equivalence relation, saying 2 edges are in the same cycle or not, right? That was the equivalence relation. So that will give me a partition of the edge set into blocks. And some blocks could be an edge, some blocks could be something like. So you have a partition like this. So this is called the block tree decompositions. But anyway, what I want to find is a place where one side you don't no longer have any other cup vertex. Okay, so so if you know the block tree decomposition, then that's the same as choosing the leaf in the block tree decomposition. So I want to choose C so that G delete C has a component X and X is minimum. Right, so among all choices of C and X, I'm going to choose C and X so that X is as small as possible. Then now what can I say? Every vertex in X has at most one neighbor in H, which means each of them has degree 2. I mean at least 2. right? So here's an x, here's c, and here's a v over h. And so every vertex in x has degree at least 2 in x. That means x has like at least 3 neighbors, 3 vertices. All right. In order to have a degree, you need to have neighbors inside x. Oh, no, actually 2. Right? Because the degree could be you have a 1 and up to c you have another neighbors. So x has at least 2 vertices. That means, and I claim that G induced on vertices of x union C is 2 connected. Why? Because if it's not 2 connected, then you have a cup vertex, right? C is here, another cup vertex separating C to the rest of x. In that case, instead of choosing this as C, I could choose C prime. Then I will get a smaller x, which is contradiction because I chose x to be as small as possible, right? So that's what I mean by choosing the leaf of the block tree decompositions. All right, so this is 2 connected. Now, so let's look at this graph. So let G prime be G induced on X union C. So that's G prime, and here's a VH, and C is the only vertex having neighbors. The other vertices here. All right, now we use the fact the graph is 3 connected. Since G is 3 connected, G delete C is 2 connected, right? So if I delete C, still have 2 connected graph, and G prime has no edges to outside world to this side, so you must have a 2 vertices having neighbors in VH. If you have only 1 vertex having neighbors to VH, then when you delete that vertex, graph is disconnected, so that's not good, right? So that means G delete C, so in other words X has 2 vertices, X and Y, such that having neighbors in V of H. Now let D be a cycle in G prime containing X and Y, because G prime is 2 connected, so for any 2 vertices you have a cycle containing it. Then that's what we wanted. So that's it. Disprove the claim, right? Claim 2. So claim 2 is to show that, oh no, not claim 2. We find the cycle D. We prove this, and that means, okay, let me use the screen on the left. Right, this means we find this cycle D, so that means we prove this wish. Oops. right? This is proven. So that means we are getting contradiction to the assumption that H is chosen to be maximal, right? So therefore, this proves the claim too. All right. Now, let's just finish the proof. Let phi 2 be a G2 circulation of G such that phi 2 of E is non-zero for edges in C, and phi 2 of E is 0 for edges not in C. Then let phi 1 be a G3 circulation of G such that phi 1E is non-zero for edges not in C, and I can only guarantee inside could be something else. Then phi 1 comma phi 2, when you combine these two, is a nowhere-zero G2 times G3 flow. So G has a nowhere-zero 6 flow. Okay, that's the proof of the theorem of Seymour. All right. So this gives a. So let's go back to the overview of the status, right? So we had this touch 5-flow conjecture, 4-flow conjecture, and 3-flow conjectures. 5-flow conjecture says that every graph without cut edges have a nowhere-zero 5-flow. And in the previous lecture, we saw that there's an easy proof that every graph without cut edges have 8 flows. And Seymour's theorem says there's a 6 flow. So what's left is to prove 5 flow. 5 is prime, so this group technique doesn't work. There's like the only group of size 5 you can think of is this G5, which is same. So that's open. How about the 3-flow conjecture? So 3-flow conjecture says that every 4-edge connected graph has nowhere-zero 3-flow. As a weakening, in 1988, Zhezhe's conjecture something called weak 3-flow conjecture. He conjectured that there is K such that every K edge connected graph has a nowhere-zero 3-flow. So since we don't know how to prove the touch 3-flow conjecture, he was asking whether it will have to increase the edge connectivity instead of 4-edge connected, right? So touch 3-flow conjecture is the case when K is 4. And the question is, can we prove it for any K bigger than 4? I mean, any number. And for a long time, even with K million, no one knew how to prove it. So it was open for 20 years. And recently, Carlson Thomason, who is the same person proving this 5-list coloring theorem, and he proved that K8 works. Okay, so every 8-inch connected graph must have noise at 3 flow. Right? That was surprising. And a few years ago, in this course, I covered the proof of this proof of this Thomason's theorem. It took full 1.5 hours. So this semester, I'm not going to cover it. But the proof is actually readable. So if you read the paper of Carsten's, published in 2012, then you can actually follow the proof. And then soon after, in 2013, there's Miklos Lovas and the Thomason and Wu and CQ Zhang. These people published a paper that K6 works. Basically on the same idea, but with the new additional techniques. And Thomason was I remember that Thomason was a bit annoyed because he could have been able to prove it 6 in the beginning, but anyway. And the reason, by the way, the reason why I wrote M Lobas instead of a Lobas is because this person is a son of the Lobas. Do you remember when we covered the perfect graphs, there was a theorem due to Lobas proving the weak perfect graph conjecture, and his son is also doing graph theory and combinatorics. And this is when he was a graduate student at MIT. He was one of the authors involved in here. Anyway, so that's another status. Okay, so this is all right. So let me write it down. So Thomason has a weakening, and then Lobas and Thomas and Wu Zhang has another weakening. Okay, and this is, as far as I know, this is the current status. All right. Now let's start a new chapter. Seven, extremal graph theory. All right. So one of the most fundamental or most elementary but important result in the extremal graph theory is the Turan's theorem. And what is the Turan's theorem? The question is, what is the maximum number of edges in a simple n-vertex graph G with no subgraph isomorphic to KR? How many edges can you put without creating any complete graph on R vertices? And here's one example. Okay, let me start with the easy case when R is 3. What can you do? So you don't want to have a triangle. And the best you hope is maybe you divide the vertex set into 2, roughly of the same size, and make a complete bipartite graph. So it's something like this. But because of parity, maybe I have something like this. This is one example where you don't have any triangle because this is complete bipartite graph, and bipartite graph doesn't have any cycles of odd lengths, so there's no triangle. And you can generalize that idea. So in general, when R is something, then you partition the graph into r minus 1 sets and put edges between different parts. And you can solve some inequality and saying that in order to maximize the number of edges in this thing, right? So in order to maximize this function ai times aj, where sum of ai from 1 up to r minus 1 is n. How to maximize that? To maximize this, you need to make sure that all the difference between ai and aj should be at most 1. So roughly, you divide things into r minus 1 sets of similar size. And that is actually the theorem. So this is the example where you don't have a KR, because if you pick R vertices, then by Pigeonhole principle, at least 2 vertices will be in the same set. Then between them, there's no edge, right? So they don't have any complete graph on R vertices. And so let's call this graph as TRN. This is called the Turan graph. Okay, so this is a graph on n vertices, having a partition of its vertex set into r minus 1 sets, x1 up to xr minus 1, so that difference between distinct ij is at most 1, and 2 vertices. It's a simple graph. In distinct xi, xj are adjacent. Okay, so that's a Turan graph. So this is, in a sense, this is T2n, this is TRN. And the Turan's theorem in 1941 says that if a simple n vertex graph has no k r plus 1 subgraph, then number of edges is at most TR. Oh, I may have to change the notation. Let's change the notation because I was... Okay, so yeah, this is T2n, right? This is TR minus 1n. Okay, so I didn't realize. So it's R, oops, R sets. Okay. So if you don't have a KR plus 1, let me say it this way. If you don't have a KR plus 1, then the number of edges is at most number of edges in the Turan graph. Okay. This is what we want to prove. Moreover, the equality holds if and only if G is isomorphic to TRN. And there are many proofs known to for Turan's theorem. Let me show you a simple proof by induction. This is due to Chekhov in 1949. So I will do the induction on n. Now, if n is less than or equal to r, then it's trivial. No graph has kr plus 1, and Turan graph is the complete graph. All right? So we may assume n is bigger than r. So suppose G is edge maximal without kr plus 1 subgraph. So what I mean is, I can assume that adding any edge to G will make a kr plus 1 subgraph. So that means I must have a complete graph on R vertices. Why? Because I add an edge, I have a kr plus 1. So when I delete it, I still have a kr, right? So I have a subgraph K, which is kr. Let me say isomorphic to K. Ooh. Isomorphic to kr. So let x be a subset of vertices such that gx is isomorphic to kr. Right? So you have a set X which is complete graph on R vertices. Now, by induction, G delete kr, G delete X has at most this many edges, right? That's the number of edges. When I delete it, the remaining you have this many edges. And what about the edges between them? Well, it's gonna be, this will be at most r times n minus r. Oops, yeah. And this is like r choose 2. So then number of edges of the graph G is at most n choose, like number of edges of the Turan graph on n minus 1 vertices plus r times n minus r plus r choose 2. So what is that? X is complete to everybody, right? X is complete. So kr is complete to everybody outside. Now what we can do is, we can observe is that this is equal to the number of edges in Turan graph, just by putting each of these vertices into distinct parts of R vertices, right? So move one over here, one over there, one over here, right? So you can move this over here, here in distinct backs, and graph is same. Okay? Am I doing all right? Let me think. Is this the correct explanations? Actually, I was cheating. Actually, I was cheating. So where did I cheat? Maybe I didn't think carefully. So here's the place. Let me see why it works. Now, why is this true? The reason is that no vertex here has more than no vertex there has more than r neighbors, because if this vertex has r neighbors, then you have a complete graph on r vertices, so that's not possible. So I should actually make r minus 1 times m minus r, right? Every vertex in G minus X has at most r minus 1 neighbors in X. That's the trick. Okay? Now, once you look at the equation from Turan graph of m minus r vertices and Turan graph of m vertices, the difference of the number of edges is precisely this. So this equality is easy to observe. Now, when do we have equality? The equality holds if number of edges of G delete X is precisely number of edges of Turan minus this graph, which is, by induction, this implies that G delete X is isomorphic to Turan graph. So, and the only way you can achieve this equality is every vertex in outside of K is adjacent to exactly r minus 1 vertices, and that can only occur, right? That can only occur if graph is a Turan graph. Okay. Why? Because, yeah, I mean, you can think of the other directions. Yeah, anyway, I think it's easy derivation. Right, so that's one proof. There are other proofs. Now, I will show you one application in combinatorial geometry. So here's a corollary due to Erdős. Let S be a set of n points in the plane such that distance the distance between any 2 points is at most 1 for all x, y in S. Then the number of pairs of points, like a pairs x, y, of points with distance bigger than square root 1 over square root 2 is at most n square over 3. And moreover, this is tight. So if you have n points, any 2 points have distance at most 1, then you can find many pairs where distance, no, you cannot find too many pairs of distance bigger than square root 1 over square root 2. And what's the proof? The proof is, let G be a graph on the vertex at S. Okay, such that 2 vertices are adjacent if the distance is bigger than 1 over square root 2. Now, I'm going to show you that G has no K4 subgraph. If G has a K4 subgraph, A, B, C, D, between any pair of them, distance is square root, at least square root 1 over square root 2. All right? Okay, I mean, the thing is, if I have a 3 point, it's A, B, C, and this, if this angle is bigger than 90 degree, and this, oops, right, I mean, if this is 90 and 1 over square root 2, 1 over square root 2, then this length is going to be, by Pythagoras theorem, it's 1 over 2 plus 1, so this is 1, right? So that means, and this length will be longer than that length, right? So if there are 3 points in G forming a K3 subgraph, then any angle formed by those 3 points is at most 90 degree, right? Now, if you have 4 points inside G having K4 subgraph, then all the angles should be at most 90. So if I have 4 points, it looks like this, or one of these two situations, right? A, B, C, D. So in this case, it's easy to see that one of these 3 angles will be bigger than 90. How about that? Oh, actually, equality doesn't work as well, right? Because this is bigger than 1/2, bigger than 1, greater than, so this is bigger than 1, right? So it's less than 90. So one of these 4 angles will be bigger than 90 or equal to 90, right? So that's contradiction. So G has no K4 subgraph. So by the Turan's theorem, number of edges is at most number of edges of Turan number. What is the number of edges here? It's going to be n over 3, n over 3, n over 3, something like this. So it's roughly n over 3 times n over 3, 3 times n over 3, right? Something like this. But to be safe, but it's actually there's an error, right? There's, depending on the n modulo 3, you have to fix it a little bit. So let me just roughly show you something like this. So this is n squared over 3. So that gives a, oops, yeah. Roughly, yeah. We need to have a floor, ceiling, right? Depending on the n modulo 3. Right, so this proves that the size of the number of edges, number of pairs of distance bigger than 1 over square root 2 cannot be too much. It's the order of n squared over 3. Now you just check this by n modulo 1, 2, 3, right? In all 3 cases, check. Then eventually what you want is One you want, oops, one you want is this. Okay, so that's it for today.